Let's talk about the introduction and elimination rules for the existential quantifier. The basic idea motivating existential introduction is as follows. Suppose that object A is f. Then surely some object x is f. So for example, if Atari is a cat, then surely some object x is a cat. So from the claim that a specific object, in this case Atari, has a property, in this case the property of being a cat, you can infer that some object has this property. Formally, the rule looks like this. If in line M of your proof, you have a sentence AC that contains one or more occurrences of the name C, you can then infer that there is an x such that AX, where in the sentence that is embedded in the scope of the universal quantifier, you replace one or more occurrences of the name C by the variable x. And you can justify this inference by existential introduction applied to line M. Now, to apply this rule properly, you just need to pay attention to one important constraint, and the constraint is that the variable x must not occur in the sentence AC that appears in line M. So the variable x may not appear in line M when you apply the rule as in this example. Let's look at a few examples of correct and incorrect applications of the rule existential introduction. First, in the top left corner, you see a correct application of the rule existential introduction. In line M, we have the sentence LAA, and you may then infer that there is an x such that LAX, and justify this inference by means of existential introduction applied to line 1. And here you see that we have replaced the second occurrence of the name A by means of the variable x, and then prefixed the resulting open formula with the existential quantifier. So this is a good application of existential introduction. Another good application of existential introduction is in the bottom left corner. Suppose that in line M, we have the sentence LAA again. You may then infer that there is an x such that LXX, and justify this inference by means of existential introduction applied to line M. So the main difference to the previous example is that here we have replaced both occurrences of the name A by means of the variable x. So that is another good use of the rule existential introduction. Now on the right-hand side, you see a bad example, an incorrect application of the rule existential introduction. Suppose that in line M of your proof, you have the sentence for all x, LAX. And suppose you then wanted to infer the sentence, there is an x such that for all x, LXX. Now, this does not work. And the reason is because in line M of the proof, the sentence already contains the variable x. Now, you could infer that there is a y such that for all x, LYX. That would be fine. So from line M, you can infer there's a y such that for all x, LYX. That would be okay. But the sentence that we have in line N is not correctly inferred. Now, existential elimination is presumably our most complicated and most difficult to understand quantifier rule. The basic idea motivating existential elimination is this. If we know that some object is f, and under the supposition that C is this object, we can infer a sentence B, then B must be true. So for example, if we know that some cat is gray, and under the supposition that this cat is called Atari, we can infer that some cat is furry, then we can infer that some cat is furry. So formally, this rule looks like this. Suppose that in line M of your proof, you have an existentially quantified sentence. There is an X such that AX. And in line I of our proof, we suppose that AC. So we effectively suppose that C is an object that satisfies the open formula AX. And under the supposition that C satisfies the open formula AX, we can infer the sentence B. You may then infer the sentence B and justify this inference by means of existential elimination applied to line M and the subproof from line I to line J. So here, one way to think about line I in this proof is that line I effectively says, let C be the object that makes the sentence in line M true. So we are supposing that C is one of the objects that makes the existentially quantified sentence in line M true. And under this supposition, we can then infer the sentence B. And so we may then infer that B must be true and justify this inference by means of existential elimination. Now, for the correct application of this rule, we need to obey three important constraints. The first constraint is that the name C must not occur in any assumptions that are undischarged before line I. So you see in the formal statement of the rule in line M, the name C does not occur. And that's crucial. So C must not occur in any undischarged assumptions before line I. It's always best to just use a new name that you haven't seen before in your proof. That's the first important constraint. And then the second important constraint is that C must not occur in the sentence to which you apply the rule existential elimination. So C must not occur in the sentence that we here have in line M. There is an X such that AX. And the third important constraint is that the name C also must not occur in the sentence B that we are inferring in the very end. So those are the three main constraints that you need to pay attention to for the correct application of existential elimination. So here is an example of a good application and an example of an incorrect application of existential elimination. Let's first look at the correct application. So on the left-hand side, you see a correct use of existential elimination. In line 1 of our proof, we have the sentence that there is an X such that Fx. And in line 2, we have the universally quantified sentence for all X if Fx and then Gx. So those are the two main assumptions on which our proof relies. And now in line 3, we suppose that Fb. So we are effectively saying, suppose that B is the object that makes our existentially quantified sentence in line 1 true. We can infer in line 4 that if Fb then Gb, and justify this inference by universal elimination applied to line 2, and then we can infer Gb and justify this inference by conditional elimination applied to lines 3 and 4. And now we can infer that there is an X such that Gx, and justify this inference by means of existential introduction applied to line 5. And then we can finally infer that there is an X such that Gx, and justify this inference by means of existential elimination applied to line 1 and the subproof from 3 to 6. So this is a good application of existential elimination. Now, on the right-hand side, you see an incorrect application of existential elimination. In line 1, we have the premise that LB. In line 2, we have the premise that some x is such that x is not L. In line 3, we introduce an additional assumption, namely that not LB, meaning B does not have the property of being L. And then we infer LB and not LB by conjunction introduction applied to lines 1 and 3, and continue to infer that there is an x such that Lx and not Lx, and by means of existential introduction applied to line 4. And then we infer that something is both L and not L, for some x, Lx and not Lx. Now, the conclusion here is a contradiction, so something has gone wrong. And we shouldn't be able to prove a contradiction. We shouldn't be able to prove that some x is both L and not L. So what has gone wrong? Well, the main mistake that we did here concerns line 3. In line 3, we effectively said, let B be the object that makes the existentially quantified sentence in line 2 true. But we are here using a name, namely B, that occurs in an undischarged assumption. B also occurs in line 1 here, and that we cannot do. When you start a new subproof, make sure to use a name that doesn't appear anywhere earlier in your proof if you want to apply existential elimination. So this is an incorrect application, an incorrect use of existential elimination.